be able to know the 5-number summary quickly and easily. As always, least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? No.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it? What happened?
Hey, what's going on, everybody? A little Stranger Things to start things out. Hair's just going pretty crazy. We're going to start up with some review here. Mewbot's already Mewbot. You got to give out some points, man. We have the reviews in the chat, and we're going to be good to go. Zaid, good to see you here. Andrew, good to see you here. And Carson, good to see you here. Review is pulled up, so let's get the review here. How are my fantasy teams doing? Looking over here. It's very important. It's a low-scoring week, but it's an even lower-scoring week for the team I'm playing against. I'm predicted to get 89 points, and their team's predicted to get 70. Cardinals defense better hang on right there. Arizona Cardinals, right? I think so. I don't know. I don't know football. Good to see Olivia here making some flashcards currently. Good to see her, Mary and Zoe. Let's throw out some more points. More points for everybody. Is Mewbot giving out those points? Mewbot, you giving out those points? He might not be giving... Oh, he is giving out points. I don't think he gave out the first set of points. We'll have to get more points. So let's do this. Happy Sunday, Luke. Good to see you here. Let's go check out the review page. Here we go. Checking out the review page. About to start up some review. Let's do this. Okay, so we got the review page up right here, and there's tons of great information on this. So check it out. Once again, if you don't know Kylie, good to see you here. We got review 2. Review 3 page exists too. We add to the review pages as the semester goes. But this is the Stat 1 review page right here. So you can see we will be adding to this as the time goes on. But there's a ton of videos. So if you're watching this later on, or if you haven't checked it out already, I've got the chapter review videos. We'll be going over these chapters, starting out with chapter 7 here in a second. Then you go down here, you've got like questions from the test. So you can go over how to do some probability stuff right here, how to solve a probability question or two, good stuff. And then you've got your speedrun videos down here that go through certain topics. So this is a really great way to review if you're not watching this video right now, but check out the review page 2 right there in the chat for you, and check that out. Okay, so let's put on our series page. You bet the Kahoot's still tonight. You bet. I know, right? It'll be it's 7 p.m. your time, 6 p.m. my time, so it'll be after this. So check out the Kahoot tonight. $50 first prize, $20 second prize, $10 third place. Caroline, good to see you. 100 points for Caroline right there. So let's start out. Tiffany, good to see you here too. Everybody in the chat. So let's go check out topics for exam 2, fall 2020. Okay, so we're going to grab this right here and kind of go through. I'm probably going to start off with some concepts. Let's put a break in the video. Here we go with the break in the video. Project 1 grades are coming out. I talked to the graders and they said it should be done by this weekend. I said, hey, we need those Project 1 grades. And so they should have them done by this weekend. I communicated to them that we need those project grades. They've been pretty good about the visualizations. And so thank you to the graders who are working on their stuff too. But it is very important that they have these things done in a timely fashion so you can see your grades. So I did communicate to the graders and they've all said to me they should have them done this weekend. Some people have already gotten their grades back. Sorry for those who haven't, but I have communicated to them, please, can we get the grades, please? And they said, yes, we are working on that. With that, it is time for some Chapter 7. Let's go check out some Chapter 7. Here we go. So what is the whole thing about Chapter 7? Like, what concept do you need to really know for Chapter 7 and 8? Who knows? A little chill music right here. Who knows Chapter 7 and 8? What are we talking about for Chapter 7? What's the concept? You should immediately be like, oh, Chapter 7 is all about this. Like, you should at least know what... One time a teacher asked us, like, what is the name of the chapter we're doing? And I was like, I have no clue. And they're like, okay, did you read the book? Did you look at it? There was a required reading. Not regression. So what is regression? We start off with regression right here. We have the following. Regression is the idea of fitting a line through an X and a Y variable. Now, both your X and your Y variable need to be what? Which these are the conditions right here. When you think about regression right here, you've got data like this. So both your X and your Y need to be what? If you're doing regression, your X and your Y need to be what variable type? So think about, like, I just had a 320 student asking about this. I was like, I think I had a quant right there. Olivia, great job. They're quantitative variables. So these both have to be quantitative variables. Almost like we're saying the first condition for regression is that they're quantitative variables. Now, what's the next idea behind this? When we fit the line to this, the idea is that the X and the Y will have a what relationship? So when we think about Q, you know the next condition. So we have two quantitative variables here. It means like height and weight. It's going to have a straight enough relationship. And that's what you see right here with this line right here. This line of best fit is going to have a straight enough relationship. So QQ straight enough. And then next we have no outliers, which means we don't want these little things down here. This is bad. It's bad right there. We don't want those. QQ straight enough, no outliers. And then what about the plot doesn't thicken? So a lot of people get confused on plot thickening. What's the deal? What's the deal with plot thickening? So if I tell you the plot does not thicken, so what is the deal? I call it plot does not thicken condition. Bad. So what do we mean when we say the plot does not thicken? It stays the same thickness throughout. It's going to be like this. Drawing some bad versions of it over here are going to look something like this. These are two bad versions of it. Bad versions. So bad versions are going to be like a line like this or a line like this. Doesn't matter which way the line goes. And you could see something where the plot gets thinner. Notice how I'm making like a funnel shape. That's bad. So that's a funnel shape right there. The plot gets thinner. I called it consistent. Yeah, it's actually called equal variance or like constant thickness. You can call it constant thickness. Greater Shiga points. This is like an hourglass shape right here, which does not have a constant thickness. So if you were to draw little bands around this, you would see like a change in the thickness. So you don't want to see a non-consistent thickness in unequal variance. There's a lot of words we use for this in statistics, but what you want to see is the plot stays the same thickness. Does that make sense? What's going on right here? The plot stays the same thickness. So how do we say this? QQ, two quantitative variables, straight enough, no outliers, plot doesn't thicken. Will this be posted if we can't stay for the whole? Yes, this is recorded. Everything's recorded live. You can even rewind live. Homoscedasticity, 100 points right there. Homoscedasticity versus heteroscedasticity. Homoscedasticity means same thickness, and hetero means differing thickness. So nice job on remembering the kind of, you don't need to know those complex words for Stat 201. You need to know what. You need to know some form of the what for this terminology for this. So you can know the complex stuff, the equal variance, the homoscedasticity, but it all means one thing. It all means we want to see the same what throughout the plot, which this first plot over here on the left shows. It means we want to see the same this. Yep, we'll have the Kahoot later tonight, you bet. In 2 hours, 15 minutes, Kahoot. Just doing a little more review right now. The same thickness. Great job, Kayla, right there. Some more 50 points. The same equal thickness throughout. Now, where do we go and investigate this a lot of times? Where could you investigate? Is that the next thing on here? Yeah, cool. We'll check that out next. Where could you investigate a lot of these ideas behind this? Where could you investigate a lot of these ideas? Where could you investigate a lot of these ideas? What is Brian drawing right now? If you make the line and make it flat and set it to 0, where could you investigate a lot of the ideas to see if there is this constant thickness? Bridget, amazing job, Bridget. More points in the chat to you right there. Bridget is right. We could investigate it in a residual plot. So a residual plot is literally taking your line and making it flat. You take the line, you make it flat, you've made a residual plot. Literally, I wish I could show it right here, but you would just take this line right here and make it flat. So a residual plot shows you all your residuals. Like, let's say I had a crazy point right here. Crazy point right here. Well, then that would show up over here. It's like over that second band, right? That same point right here, when you make the line flat, is going to have a what residual? Tell me positive, negative, 0. What does it mean that this has a positive residual? And this is kind of some more concepts we're going to be talking about here as we go through just some concept review. What does it mean for something to have a positive residual? For something to have a positive residual, like this is a good, like you're writing down things. When something has a positive residual, which this has, that means it's what? Tiffany's got the formula in the chat. So since this has a positive residual, 50 points, Tiffany right there. Since this has a positive residual, it's above the line, exactly. So when you think about the line right here, let's just focus in on only that point right there. Its residual is going to be this, which is the same distance right here. It might be a little scaled differently, but that's its residual right here. So its residual is calculated from the actual, which is like, what was their actual y value right here? We don't need the homoscedasticity anymore. So we'd go over here, and we'd calculate its actual y value to maybe 100, and then we'd need its what y value. Over here, the line would give us a value of what for the line. So the line gives us a what. Kind of you're on the right track, Casey. The line gives a what value. Not a y value, but the line would give a... And let's say this value over here is something like 60. Just making these up. It's going to give a predictive value. Great job there, Finch. So it's very easy to calculate right now. What is the residual? You should see it. And if you know how residuals are calculated, it's just how much the model misses by. And then it's pretty easy to tell that this one's positive because it's above the line. Remember, it's going to be the actual. So this right here is the actual. Where is the point actually at? Like, where is the actual y value? This is the predicted. And it's 40. Great job right there. Excellent work, everybody. Some more points in the chat. Just keep practicing right here, reviewing these concepts that we've learned a while ago now that we just need a refresher on, that we can see what a residual is. And the residual concept is called E. So the formula is E equals actual minus predicted. I like to say residual equals actual minus predicted. Some people call it the observed, which is all right. But if something is above the line, it'll have a positive residual. If it is below the line, it'll have a negative residual. And if something is on the line, anything on the line would have a residual of 0. Keep asking questions. How would we interpret a residual? Let's say this is a test score, maybe. This individual scored 40 points higher than they were predicted to score. Does that make sense? So the interpretation of it, which don't worry, is not on the test. But we would say the person scored a 100, which is 40 points higher than they were predicted to score. If you look, here's their prediction value of 60, and the actual value is 100. So they scored 40 points higher than they were predicted to score. Do we get a formula sheet? The formula sheet should be on the Stat Tool and Review page. MuBot, show us where that's at. You can print off the formula sheet or you can write it down. Just make sure to show it before the test. Good stuff. What is so special about this line of best fit? It's really just a conceptual question right here. I'm bringing this over to a new page. What is so special about this line of best fit? What's so special about it? Why do we call it the line of best fit, the line of least squares? Oh, thank you. Terry does such a great job with those. Thank you to Terry. Not thank you to me. The line of best fit. We could take data points like this right here and put any line through it. You just draw a line wherever you want. You just say, I draw a line. It's the most, basically, and so it's the best line, and it reduces the sums of the squared error. It gets into more mathematics on the naive model and our model and the reduction in sums of squared error. But Bridget, amazing job. We're making Bridget a mod. We're just going out here on a limb. Bridget, you're on mod 2. Thank you, Bridget, and some points for everyone right there. The line of best fit has the least error. This right here is basically error. We won't get into whole sums of squared error. We get into that in like 320 in upper level classes. But you can think of this as error. If you have a miss for the model, you could take your residual and square it. And so the least squares basically means the least error. And the reason does anyone have any idea? And this is a great question because this goes to 201. Why do you think we square the residuals? And I want you to just think about this model right here. Why do you think we square the residuals? Because what would residuals add up to? Which this is a theory question sometimes on the test. If you had here residuals, which this line would go through like this, what do all the residuals add up to? And this is hence why we square them. Why we do like a sums of squared error, not just a sum of error. Marjorie got it. They would add up to 0 because does that make sense? Some are below the line, some are above the line, and that's why we square the residuals. That goes into a little more theory than we do in 201, but conceptually with those points right there, it should visually make sense that they're going to counterbalance and the line's going to go through the center of the data. And because of that, if you were to add them up, you'd get 0. So we actually figure out the squared error when we figure out how much error there is, rather than like, think of it, the sum of the squared error, rather than the sum of the error. I hope that makes sense conceptually. Correlation here might not be 1. Correlation is going to be positive for that. It might be like 0.6 or 0.7. Probably not statistically significant with that small data. Olivia and everybody, great questions. I printed the formula sheet out, but it cut off the Haslam stamp at the end of the page. Oh, that's fine. That's fine. Don't worry about that. Haslam can't speak for the Haslams, but we'll assume they're okay with that. Given the jump output, write the regression model with accurate variable names Okay, so let's make some jump output here. Who's ready here? 2 seconds. Let's make some jump output. Everybody's practicing along with some jump output. Okay, what kind of variables am I going to need, everybody? I need some help with what kind of variables. Help Brian out. Say, Brian, you'd better pick what kind of variables right now. Brian, you better pick these certain... Oh, Zoe knows right there. QQ. Better pick 2 quantitative variables. You're not doing regression. My people in my upper level classes ask me this to say, why can't I get a regression? I say, you don't got 2 quantitative variables. Here we go. What issue do you see with this? I see one issue pretty instantaneously here at the end of the model. I can make a residual plot, which is going to take that line and make it flat too. Got to go down here for the residual plot. But I see probably a little bit of an issue at the end of that model. I'm thinking, and there's the residual plot. Remember I said take that line, make it flat? Can we get it so it just shows that? Guess we can't. Yeah, we can here. I want to show them both on the same screen at the same time. Remember I said take the line and make it flat? You see the line right here? You see this point right here? It's that point right there. You see these 3 points over here? These 3 points here. Does this make more sense when I say a residual plot? Take that line, make it what? I want to say in the chat. Residual plot, take that line, make it what? You see the plot, you see the residual plot, you take that line, you make it what? Then we'll do some interpretations here. You take that line, you make it flat. Marjorie knows right there. You take that line, you make it flat. Can you say the interpretation so I can write them? You bet. We'll begin to that here very soon. Very soon. Interpretation. Everyone 100 points. Keep it up. Take that line, make it flat, make it a residual plot. Residual plot literally just shows you all the residuals. You can see here positive residual. Residuals close to 0. Residuals close to 0 are basically on the what? These are residuals close to 0. They're very close to the what? Every residual that's very close to 0, you can see all them here. You can see residuals close to 0. All the residuals that are close to 0 are points that are very close to the what? I mean, these are positive, these are negative, and these are super close to 0. All the residuals that are very close to 0 are basically on the where. Like these are super negative down here. And you can see them. There's the points up there when I highlight them down here. I mean, you might just have to understand if it's a residual plot. Like a lot of people see this sometimes and they say, oh, that's a regression plot. And it's like, no, that's a residual plot. Because one, it says residuals right here. It's set to 0. It's the line flat. So a lot of times people don't understand conceptually why we have a residual plot. So all those good answers right there. So you should know why we have residual plots, why we use them. And I see an issue with the nonlinearity here at the end. So one thing I want you to be able to do is to be able to write out the regression model, which we do have the answer for it. Let's go to the parameter estimates, and we'll do interpretation of this right here. So we're going to write the model and interpret it. Okay, let's hop over here. So, because we'll do some interpretation in a second on that. Okay. What is the intercept called in notation? And this will help us out with the interpretation here in a moment. We're going to practice interpretation right after this. What is the intercept called? What is the intercept called? Tell me the name of the notation for the intercept. We're going to forget algebra for a moment. We're going to forget algebra. Pretend you never learned algebra. What is the intercept called in notation? What value do we assign to it? What do we call it? Close, Marjorie, close. You're on the right track. It does have a 0. The intercept is B0. This is B0, and this is B1, and this is the name of your X variable. So maybe I should put them closer. It's just hard to write next to that output. This value is B0, and this value is B1, and this is the name of your X variable. Like, that is the name of your X variable. So when we write this out right here, I thought I made Bridget a mod. 2 Bridgets? Confusing. Okay. So y hat equals B0 plus B1x. This is the constant formula right here. Brian was predicting what with his model? Brian was predicting, you don't got to tell me the whole variable name thing over here, but just tell me the short. I mean, like, tell me that. Brian is predicting what for his model? Brian is predicting what for his model? We're just writing the equation right now and seeing how the equation works, and then we'll interpret it next. Brian is predicting what for his model? Brian is predicting, so that's the y hat. Y hat is the name of the variable we're predicting. It's just like a y variable, but the hat means predicted. If you want to get really fancy, it's technically, like, it's not the word y hat. You have to go to here to equation, accents. You gotta squint at the screen because it's hard to see. And it's that right there. Height, exactly. Great job. And then put the context in Olivia. Olivia, great job. Some 50 points right there. Olivia, you're on right on track, following along. So all we're going to do is going to plug in the names of the variables. We have here predicted height. That means predicted height is equal to the estimate of the intercept. We're going to round this up just for the time being. Carry decimals as it says on the test. And then we're going to multiply this out right here by the x variable, which is weight. That's just a x04, like the fourth x variable. So we have right here an equation now. And this, once again, is B0, B1x. And what's really helpful is the B0 and B1 give us good information on how to explain these. Let's write down our interpretations right here, which are super important. Let's put this down. Put these on note cards to practice. I cannot state this enough. You ready? Here we go. Put these down. Somebody try to interpret these as we practice right here. I just love playing a little music in the background. Just chill music. Okay, so I need some slope interpretation right here. People are going to lose points on the test like crazy on these. Slope. For each 1 unit increase in x, we expect y to increase / decrease by b1. There's slope. I want to get this all on one page. There's slope. Intercept when x is equal to 0, like b0, we expect y to equal b sub 0. Okay. Wow. Okay. For each 1 unit increase in x, 0. We expect y. Who's got some interpretations for me on these? Who knows how to do these? Need some help. Who's got interpretations? Oh, looks like Olivia's got some. We'll see. Okay. For each 1 pound increase, we expect the height to increase by 0.074 inches. Inches on average. Great job, Olivia, right there. When weight is equal to 0, we expect height to equal 56.3 inches. Inches. Make sure to put the units on there. Olivia, 100 points. And then, Olivia, what would you add on to there about that intercept interpretation? With the intercept interpretation, you're saying when weight is equal to 0, because think about this, you're plugging in weight equal to 0 right here. You're saying when weight is equal to 0, I would predict or expect someone's height. Perfect way of saying you predict or expect. These are fun. What do you notice about this? If you say when someone's weight is equal to 0, I expect them to be 56.3 inches tall. What do you notice about that? So Olivia's got the interpretations in the chat. Try to do it yourself. A lot of people are going to, I tell you where points are going to be lost. I'm just flat out telling you these interpretations, if they're on the test, wink, wink, wink. People are going to lose points here. Oh, yeah. Oh, geez. Some grader's going to be mean on this. On average. I hate that. That's stupid. Sorry. Some grader. We're saying what we expect. So it could be, and it's not possible to be 0 pounds. Someone, please put that on average there. Some graders take off for that. I've never been, if we're going to get very exact, there is a more exact interpretation we use in 320. So I've never been a big fan of the on average part of what some people think is required. It's where statisticians argue over stuff, but in 320 we get into a more very mathematical exact interpretation. So this is for 201 right here, where it's kind of more general purpose. So that way I've always thought we should be a little more forgiving. But with that said, there are very wrong interpretations to do. So let's do one more here, because this is where I promise you people are going to lose points. Yeah, you could. You just a little sprinkle in a little on average there. It never hurts. You might. Grader can't get mad for that on average. It's when you say expect, that means on average. Does that make sense? After you get done with this review, can you post these notes? I think so. Mm-hmm. I'll post them to the website. So I would be just very precise. Let's try to do this. So I need some people to put some interpretations in the chat. Here's where you get your practice. I'll tell you if it's right. Let's make an interpretation right here predicting let's predict how many hours you sleep at night to predict your GPA. Oh my gosh, what have I done? One of those was categorical. Really? How is GPA categorical? It's logistic regression. There we go. Okay, that's fixed. That's what happens if it's not QQ. So it was not properly coded. It's like, why did we get logistic? Okay. Interpret the coefficient. Oof, look at that. Love it. Interpret the coefficient. Hey, Kayla, good to see you here. Interpret the coefficient of the intercept. It'll make it look nicer. This is pretty interesting. I find this model actually rather interesting. Interpret the coefficient of the intercept. While I make this model look nicer, interpret the coefficient of the intercept. What does the intercept mean right here? Who's got my intercept interpretation? If you need to see, let's take the equation and paste it in here. So here's the linear fit. All this would be obtained from down here also. So who's got my interpretation of intercept right here? Totally different model right here. But who's got my intercept interpretation? When hours of sleep, night 0, we expect GPA to be exactly. Marjorie just crushing it right there. Great job. You might throw a little on average on there. Please tell me if you think the graders are mean. I'm always pretty nice. I'm nicer than the graders sometimes. Please tell me whenever you think the graders misgrade. When a student gets a 0 hours of sleep per night, not be careful with the wills, Bridget. We want to say we expect. We would say students who get 0 hours of sleep a night, we expect. And you might say that kind of also going outside the model because you can't get 0 hours of sleep a night. And then the expect is kind of key. The one word I'd get a little bit saying will, because think of what the model does. The model makes predictions. We're not saying what will happen. We're just saying what we predict or expect. Does that make sense, Bridget? Bridget, excellent work right there. Great practice. But now be careful. What's it always? So Ashley, here we go. Good practice. It's always a what unit increase in X. It's always a what unit increase in X. So now we're going to talk about the slope right here and say for each additional what, we would expect somebody's GPA to do what? Because we're predicting GPA. It's always for a 1 unit increase. So this is always a 1 unit increase. So for every 1 hour per sleep a night increase, we expect the GPA to increase by 0.004 on average. Olivia, great job right there. You got it. So a lot of people will use the intercept down here. You're only using B1 right here. Please note, here we'll kind of highlight a few things in here. But the B1 is right here, and that is B1. The Y variable is right here, and the Y variable is right there. Y variable is right there. The X variable is here. We're just going to highlight. And the B0. The B0 is right here. And hopefully that makes more sense right there. Practice this on your own. Look over lectures where we've done it, but plugging in and making a sense that makes sense right here. You'll also notice that this is not a very strong slope and was not statistically significant. For each 1 hour increase in sleep per night, we expect GPA to increase by, and then maybe throw on that little on average right there, a little salpe on that. But that's got it. Excellent work. Good review of that. Here, let's hop to the next one. I need to combine these all into one sheet. Knowing the B0 has no logical interpretation. Why does this not have a logical interpretation? Because if we talk about the intercept here, we're talking about people who what? Why would this have no logical interpretation? If we talk about the intercept here, we're talking about people who what? Why does this really have no logical interpretation? Because we're saying when X is equal to 0. Notice the coloring. When X is equal to 0. So now we're talking about people who what? Exactly, because it's not like you don't get, it's not like you sleep 1 hour a night, 0 sleep, you get no sleep. You just, for people who don't sleep, basically, like people who sleep on average 0 hours a night. So it makes, it's people have to sleep, unless I've been lied to, people have to sleep. We did some interpretation right here. We did the, know the difference between Y and Y hat. So where are the Ys and the Y hats coming from? So where is Y and Y hat coming from? So Y's are where? What do the Y's represent? So it says we should know the difference between Y and Y hat. So where does Y come from? Where does Y come? Y hat. Y is the actual. So if I tell you Brian weighs, we're predicting Brian's height right here, or weight. Sorry, predicting Brian's weight. If I say, we'll draw it down here. Good. We're predicting Brian's weight. And I say Brian actually weighs 170. So that would be a y value. So Brian might be here-ish. So Brian actually weighs 170. But Brian was predicted to what? I want you to think about up here on the line. Brian would be predicted to what? So y is going to be where I'm actually weighing. Like I actually weigh 170. If you were to go over here and be at 170, that'd be 170 right there. So I actually weigh 170. Like that is my actual weight. So, but Brian is what? I was predicted to weigh more, and the predicted value here might be like 185 or something. So what is Brian's residual right now? If you were to calculate Brian's residual right here, so what would Brian's residual be? That's the y hat. So what would Brian's residual be? Be very careful. There's a little small error that happens right here. Close, Ashley, close. Ooh, careful, careful, careful. Think about how these work. Careful. Brian's down here below the model. -15. Olivia and everyone. Tiffany, great job. 50 points. -15. Remember this always, that this is the negative residual zone. This is the positive residual zone. And anything on the line has a residual of 0. It's just a very common error. I switched it up this time where it was a negative residual. Negative residuals means the actual is below the line of prediction. No, it's a good catch right there. It's just good practice. We see more examples with this. And we just practice, practice, practice. Here, I'm going to make a new sheet so we can only focus in on the next topic. Be able to use a regression equation to estimate of a y for a given x. Just making predictions right there. Be able to calculate and interpret a residual. We did that a lot. Be able to interpret residual plots and spot problems. Be able to find R. And yeah, let's do this. So, and we're just trying to cover as many topics as we can because there's a lot. Okay. So whenever you get R and R squared, which your Canvas content talks about a lot, this one. When you get, so anytime it's under the line, it should be negative. Exactly, because then the actual, if this is the point, the actual is below the prediction. Remember, actual minus predicted. So the predicted would have a higher value, so actual minus predicted. So below the line means negative residual. If I were to draw you a plot like this, and I were to tell you that R squared is equal to 0.81. So can anyone tell me what R would be for this? R squared is equal to 0.81. So what is R? If R squared is 0.81, then R would be what? So think about this. You want to get R from this. So you're going to have to take and do a little bit of this. But so R is correlation. R equals correlation. And R squared is percent of variation, and Y, percent variation explained. It's a slightly different concept. And how many people did I trick? Ah, great job, Bridget, right there. Bridget, you're doing an amazing job. Bridget saw it. Why is it negative 0.9? Isn't it plus or minus? When we do a square root, don't we do plus or minus? So why is it negative? And catch this. So what must we do? This is on a Canvas content. Great job, Luke, right there. So why is it negative? It's a negative line. And so you can go either which way on this. Now, if I gave you the correlation right here, it'd be much easier. If I told you correlation is equal to negative 0.90, well, then how would we calculate R squared? It's just R squared. Great job, Ashley, right there. You're 100% right. The direction of the graphic. And the slope also can indicate it too, because the slope tells you direction of correlation. So many people practicing. It's a Sunday and we're here just practicing statistics. We're out of coffee though. So now if that's negative 0.9 R, which is correlation, R squared is going to be what? Great job. Now that we have R squared calculated, I would like for you to, this is a GPA and video games. Sorry, video games. We're almost done with Nathan Drake 4. Video game hours. Sorry. I get to say this because I'm a gamer. I'm a true gamer. So to get R squared from correlation. Exactly, Olivia. Yep. That's how we did it right here. Boom. You square it. Be careful when going backwards, though. When you go backwards, that's where usually the error happens because people forget to check the direction. So how would we interpret this? How would you interpret this R squared right here? So the R squared right now is the following. I'll take a moment, let people solve it. This is the R squared right here, derived from just squaring R. When you square the R, you get the R squared. So how would we do this right here? Oof. How are we going to interpret this? Start that interpretation music. How are we going to interpret it? I don't know if there's an R-squared interpretation on the test. Might be. How am I going to do it? Great job, Olivia, right there. Olivia just crushed it for some 50 points. You got it, Olivia. Blank percent of the variation Y is explained. So remember, R squared, it's not going to be about strength, direction, form, unusual features. Bridget. I thought I made Bridget a mod. Maybe I made 2 Bridget mods. Great job, Bridget. So you need to take the R squared value. Remember, it's percent of variation explained. It's not the same as correlation. It's not correlation, even though it's squared from correlation. It's a value between 0 and 1. R squared is between 0 and 1. So R squared is contained in the interval from 0 to 1. It can go up to those values, where correlation would go from -1 to 1. Because think if you square -1, you get 1. It doesn't matter the direction. Rock?
It doesn't matter!
It's still perfect correlation. So now we take our Y variable. Blank percent of the variation in Y is explained by the variation in X. And we take that X variable right there. And there we go. So great answers right there. 81% of the variation in GPA, you could say, I would say is explained by. I might say explained by. A grader should be okay with that. Or a lot of people saying do. Is doing the notes? All right, do. 81% of the variation in someone's GPA is explained by the variation in their video game hours playing. Should we put these on flashcards? I put this on a flashcard too. Yep, doesn't hurt. Put the interpretation of the flashcards. Best way to practice them. Just have them down, be able to practice and do the interpretations. Good stuff right there. We just did it right there. Percent variation. Do not interpret the. Yeah. Okay. Well, so does playing video games cause people to have a lower GPA? No. X and Y never have a causal relationship unless we do some sort of experiment to show it. And that's been a review of linear regression, which does involve some correlation topics. Let's hop back to the main screen. Who's ready for some Chapter 8? Who's ready for some Chapter 8? Chapter 8's a short one. We got some Chapter 8 fans in the chat right now. If you're a fan of Chapter 8, let me know. Whew, it's going to be a short Chapter 8 here. Who's a fan of Chapter 8? One person? Woo, Mary says. Mary's a huge fan of Chapter 8. I think there's like 20-ish. I got to review that. We'll probably end a little bit before I do Kahoot because I got to make sure everything's lined up for that. Should be pretty easy. Isaac, oh my gosh, so many fans of Chapter 8. I didn't even know Chapter 8 was such a big fan favorite. Just like Mewbot over there. Mewbot, you doing all right, man?
I am Mewbot.
He's chilling out. He's good. Let's over to the main screen and do some Chapter 8. Okay. So understanding extrapolation. What is the one letter you hear me? Hey, Blanca, good to see you here. I agree with you, Marjorie. Those are tough chapters. What is the one word you hear me say when you hear me say extrapolation? Extrapolation. Extrapolation. Yes, extrapolation. That is the one letter you should focus in on. Who can give me a definition of extrapolation? Extrapolation is when you try to make predictions with your model that go outside the what boundaries of the scope of the variables. Like if we go here from 0 to 20 hours student study, and we say like, how does study hours, so let's put here study, increase grade. And we have students who study between 0 to 20 hours, and we see kind of a linear relationship on grade. Well, you say, wow, if I were to study, a ridiculous amount of hours, then I should put it in green if I want to do the good one. This is a good model. If I were to study further outside of here, I'm just going to make a ridiculously high grade. So with this, oh yeah, definitely. Yep. Thank you so much, everyone helping out in the chat. And sorry if it took me a while to get the videos labeled. I should be back on track now. You guys know, crazy week 2 weeks ago, but I'm doing way better. So back on track, getting those things out here. Man, we need more quotes. Bitch didn't even know we got jokes. People don't even know we got jokes. Mewbot knows Mewbot knows quotes and jokes these days. So explain to me, I want you in your own words to talk to me about some extrapolation. Extrapolation would be somebody using this model to do what? There we go. Got to look nice. I don't know if there's 6. I think there's like 4 jokes. If you come up with some good jokes, tell me and we'll put it in the joke bin. Oh, is there? Oh, yeah. Maybe there is 6 jokes. There apparently is. I didn't even know that. So tell me about some extrapolation right here. Oh, Bridget already said go past x variables. Yes, sorry, Bridget, I didn't catch it. Extending the boundaries of the x-axis. Well, kind of. You're on the right track. So it's using saying we want to plug into our model something like 28 hours as an x. So now the model would go up here and make a prediction that's outside the scope of the x. So someone says, predict my grade on the test if I study 28 hours. And the model has to extrapolate beyond what it was created from. And you can extrapolate on low sides. Like this one would not have a low extrapolation here. I think some of the other models we looked at could have a low extrapolation. Where is this model? Oh, and see like the intercept. Where would this model be extrapolating on the low side? Like this model is not really meant to make predictions below a certain point. It doesn't have data there to help it make predictions. This model right here is extrapolating where? Oh, you want to find that one using those equations. And thank you, everybody, helping out people in the chat. Below 4. 4 is the lowest value. 4 is the lowest value. Does that make sense right here? The model goes from this point, and so there is no data, even though this kind of goes to 3 right here, the data ends right here. So the data ends at 4. So below this point, the model is extrapolating if it is be used to make predictions. You can mathematically solve for negative numbers, but those just don't even exist. Like you can't sleep negative hours, but the model can, it's a math equation. So you can just plug in negative numbers down here. You'd be like, I want negative 999. Well, you could do that. You just say, let's go here and put a minimum of negative 999. And there you go. Wow. Now you're going to get the very low GPA. This is a ridiculous extrapolation of the model. You remember how the line looked flat? Now the line doesn't look so flat when you look at it in this sort of relationship. But this is not how we should do regression. This is ridiculous. This is horrible. This is a huge extrapolations. I think mostly. So be ready for those interpretations. Don't forget to write out your interpretations really good. That's my GPA. That's my GPA too right there. 50 points. You know what's up, Marjorie. We're both right there on that struggle bus. It's my high school GPA for sure. Hey, Marjorie. So we know what extrapolation is. Extrapolation is when you make predictions outside of the x's of the models. So it's using an x value that's outside the boundaries of your x to make predictions for the y. Don't do that. Bad idea. Groups and residual plots. We've never asked a question on the test on this, but I'll just in case. I don't know, so I might add something that I didn't say. What you can have right here is groups like if you were to look at a residual plot and you were to see something like this right here, you can actually have groups and we can actually fit 2 separate lines. I cannot imagine, this is a very small portion of the notes, but if you did have this, you would fit 2 separate lines. I've never seen a test question come from this, but examining residual plots right here, if we were to see groups, then we could probably do something to fix the regression. That's more of an advanced question, gets into indicator variables and stuff we don't cover. Highly doubt questions will come from that, but do know how to examine residual plots. We covered that on chapter 7. Correlation is not causation. If I were to tell you something like one of our classic statements right here, just we can go with a classic one. The more TVs you own, we do see people living longer. This is no joke. If you own more TVs, you generally live longer. And if you live longer, you generally own more TVs. Never say never. I know, right? It's kind of like, if it were to appear to be like a 2-point question, I don't think it's going to appear. I don't recall it being on there anymore. Lurking variable. What lurking variable is there? You're right. There's a variable here. And what do we mean by lurking? There's a variable that's actually controlling for this. What we have right here is an X variable, owning TVs, like how many TVs you own, and a Y. And there is a relationship. The more TVs you own, the longer you live. And the lurking variable in the background of here is probably money. And money is probably the reason people are living longer. And then TVs is probably like you have more money. So we call this almost like a Z variable right here because it's lurking. So the lurking variable right here is probably the one impacting it. Higher sums, SES. Not some squared error. Why is my brain not working on SES? You can afford more healthcare. Exactly. If you can afford more healthcare, you can afford more TVs. And so then it looks like people who have more TVs live longer. but the TVs aren't making them live longer. So you don't see this lurking variable a lot of times. There's ways to control for it, but you won't see the lurking variable, which is the Z variable. I just saw this in a book one time a long time ago where it had like, is X impacted by Y, or is Y impacted by X? Or is there some third variable that is actually the go-between between them, that like you have more money, you have more TVs, you have more money, you live longer. So then it looks like if you have more TVs, you live longer. So pretty good right there. Lurking variables and how they explain correlation that is not due to causation. Identifying outliers in a scatter plot. Let's go look at one. Let's go look at scatter plot. This one right here, you might think it has a bunch of outliers, but is anything real? That's what we ask in statistics. Statistics is such a cool discipline because it's like it's science. So you never claim you're right. You just claim you've got a good idea of something. Great job, Kelsey, right there, getting to the top tier. Got some people before test 2 at the top tier. We love that. This is probably your most extreme outlier right here. And if we go to the residual plot, you notice it right here. Very good to understand that we can see outliers. Once again, what do you think Brian's biggest issue? I don't love this as a test question, but you can look at the residual plot right here. What do you think Brian's biggest issue with this regression is? My biggest issue with this regression is going to be, what of the QQ straight enough, no outliers, plot doesn't thicken. Everything's not exactly in statistics. All models are wrong, some are useful. That's one of our favorite quotes from George Box. All models are wrong. This model's wrong. All models are wrong. Nonlinear, great job. Marjorie, I agree with Marjorie right here. That's actually the issue I see. I see a nonlinearity issue. You see here at the end where the line is not going through the middle of the points. That's also noticeable right here. I don't know if there really is a plot thickening issue, but we see this right here. I will mention this just slightly. What's really great about this, and this is survey 11, so just 2 seconds here, humor me. But we have ways of checking all of these in upper level statistics. Let me attach it so I can actually write the variables. We actually have statistical tests for all of these. So if you end up taking another class, we do the same sort of ideas. XO3 and XO4, XO3 and XO4. We're predicting height, I think. XO3 height. We will be right back in a moment. Wait, there it is. And we can actually check it. So we can, really? We can run a test right here to check it. And it actually completely fails everything. So this is the same sort of idea you just saw done for 320. So if you do take regression with me or someone else, you will see the same sort of stuff. Oh, thank you very much. This is still test 2 and just showing how we might do it in another software. And what we do need to know, so we don't need to know that, but we do need to know, looking at this plot right here, do you see how the line is not going through the data right here? Does this make sense? Like their linearity, which is the same exact thing you see in Jump right here. These are the exact same plots. This plot right here, I just made it in a different software package. But notice how the line over here at the end especially is not going through the middle. That's probably one of my bigger concerns, but there are other issues like with the equal spread, the homoscedasticity. So there's a lot of issues with this one. Looks to be a lot of issues. Normality of residuals also has a problem too. There's a QQ plot we talked about that on test 1. So anyways, we will not be doing that for test 2. We're going to hop back to the main screen and do another chapter here. So I do like to point this out, that the things you learn in 201, they're going to be used in other disciplines too. A lot of people tell me what's really great. So I'd say the linearity is one of the problems. Usually on the test, we make it a little more clear, Mary. Does that make sense? Like we usually ask a question where it's like pretty obvious, especially in 201 where we're not actually going to compute a p-value for the test. In 201, we try to make it very, very clear by saying like, oh, look at this one. And it's got like this. It's all spread out. Homoscedasticity means it has the same equal spread. It should the point should be generally around the line in an even sense. That is, the plot doesn't thicken. That's actually a good thing. You don't need to know that word, but think of it, homo, same scedasticity spread versus hetero, different scedasticity spread. So remember, plot does not thicken. It's going to like stay a same equal thickness throughout. Does that make sense? Like, does the plot, here, I'll show it in the background right here. Does the plot have about an equal thickness? Like if you look, like the thickness would be this right here, except for at the end. It might have some problems at the end. At the end, it gets a little bit wetter. At the end, at the end of this model, the plot looks to get a little bit wetter. Like if you go like this and you're thinking about how thick it is, like how spread out it is around it, at the end, it looks to get a little bit wetter. And that's where the linearity breaks. The line's not going through the middle of the data anymore. So the thickness is how far out it is away, like the spread around it. So the thickness is this, and then this thickness goes to this. It gets tighter, right? So then it's not of equal thickness. So there might be like it's more spaced out here and then it gets a little bit thinner. So there might be some problem towards the end of the model with the plot getting a little bit thinner. Exactly. And so is there a problem? I'd probably do something easier to see on the Stat 201 test where it's like more obvious. Where can we also notice this problem? Please once again say it with me. Where can we also check for things like the nonlinearity, also the thickness? Do you see here the thickness of it? Where can we also check for these problems at? Where can we also check for these problems at? Where can we check for like equal spread? Also see the linearity. We often have to look for equal spread, the residual plot. Exactly, the residual plot. So the residual plot shows us a lot of the same stuff. Let's do another topic. Here we go. Hop in here to some decision trees. Decision trees. Time for some decision trees. We're going to make a decision tree. Oh, can't you wait till we get to chapter 13. Put on this music right here. Let's hop into some chapter decision trees. Here we go, chapter decision trees. Okay. So when it comes to decision trees, what kind of variables go into a decision tree? What kind of variables go into decision trees? Like what variable type? What variables go into decision trees? What variable types can we use to make decision trees? Categorical, Categorical X, categorical Y. Yep. Great job, Blanca, right there. Crushing it, Blanca. 50 points right there, Blanca. Blanca summed it up quite well. Categoricals, less than 20 levels is subjective. You don't want but Blanca's on the right track right there. Like is it exactly 20 levels? Categorical variables that do not have too many levels. And quantitative variables, any quantitative variables, but not identifiers, as Olivia says right there. And we can do multiple quantitative variables. We can do tons of quantitative variables. We're just not going to put in identifiers or categorical variables with too many levels. So right there. So how many Y variables? One Y variable and tons of X variables. A decision tree is an algorithm. So when you want to predict something, you go to predictive modeling and you go to partition model because it's going to group the data together into like-minded individuals or things. Exactly. 20 levels is a little subjective. We just don't put in categorical variables with tons of levels. Like, is it 12 levels? So you see right here, do I have any categoricals with a lot of levels? I don't think I do right here. Do we have favorite phone app? That's one of them with a lot of levels. Is this in this data set? So let's predict. Let's predict if somebody, you see satisfied away is miscoded. Oh, no, that's correct. That's correct. Let's predict if someone's satisfied with their weight. This might be pretty interesting right here. So we're going to predict, does that make sense? We are going to predict if somebody is satisfied with their weight. Now tell me, Brian did not include a what variable in his tree. Oh, you want to do that next? Let's do that next. Let's do that next, Marjorie. That sounds cool. Let's do that next. What people use to attract people. So Brian did not include the what in his decision tree. Brian did not include the what. Like, good practice right here. We just covered it. Brian did not include the what in his tree. Let me see if there's other things. I did not include the identifier. That says it's an identifier. Identifier not included. I don't think there's any. We'll find out the hard way if I included something with too many levels. It'll show up and create problems. So probably I didn't. I'm doing how many Y variables? Just tell me how many Y variables. That's not the Y's. Those are the X's. The X's are going to explain. Great job, Tripatita. Good to see you here. How many Y variables am I including? One Y variable, and then what do I have? And look, that's quantitative, that's categorical, categorical. Red means categorical, blue means quantitative. I've got tons of X's, and I've got one Y. Let's go check out this decision tree right here and see it. We're going to color the points. We can color the points because this is categorical, which means we're asking a response question that is like groups. And let's see here. Let's do 3 splits. Someone emailed me about this. You did have 3 splits. I'm going to fix that. Sorry, got to reply to more emails. You got it. Okay, so this is whether or not people are satisfied with their weight. And the number one thing, which is the most important variable in this tree, was what about people being satisfied with their weight. And it just, sometimes the world is how it is when you see statistics. This is real data. This is 10 years ago. Getting old. Gender right there. The number one thing. And it's hard to see. It's like there was one female. How can I go view how many females are in this sort of group, or that female went over here? How can I view, and you are correct, the number one split here, which is the first split, is the most important split in the tree. It kind of determines where the rest of the tree goes. How could I go and view that one or maybe two individuals? I think it's one, but I can't really tell yet. How could I go and view that individual? How could I go and view that individual? Who knows? I'll show you some hints. I don't want to go to it yet, but look at the output on the screen. What could I go to? It should be on here. There it is. About a third of the way down. What could I go to view that individual? Not split history. Good guess right there, Olivia. The leaf report. The leaf report is going to show us. Great job, Casey, right there. The leaf report. Great. So I think I hit the points twice or something. The leaf report. There's actually 2 females in that group. So there's actually 2 females in that group. Now let's go ahead and label our output. This is where a lot of mistakes are made. So we're going to go ahead and label some output right here. And let's go grab this and label this output. Whenever you get output like this, you know what? We're going to go super label output. Okay. Can I get it all on one screen? 2 seconds. Or could I put the leaf report over here? 2 seconds. I'm going to try to get it all on one screen. Ooh, look at that. Look at that. Watch me now. Okay. Let me screenshot this and let's show all of this output and make sense of it as a review right here. Okay. We're going to bring this over here and let's show it. Now, whenever you get this output, I highly suggest labeling it. So when you're, oh, it's almost good because I'm in the corner here. We'll zoom in on it when we need to. This right here, whenever I label this output, go. We already have black. Well, now we have 2 blacks. This is leaf 1. This is leaf 2, leaf 3, leaf 4. Which leaf has the most people in it? Which leaf has the most people in it? Leaf 1, leaf 2, leaf 3, leaf 4. You can look at it like a mosaic plot. You can use the widths at the bottom. Good review of other topics that are not quite on this test. But which leaf has the most people in it? Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 2, it's just the widths on the bottom determines the size. 2 is the biggest. 3 is the second biggest. Maybe 4 and 1 are of similar size. When you go down here at the bottom, leaf 1, leaf 2, leaf 3, leaf 4. How many people are actually here? We're trying to make sense of the output to see what we see and understand what we're seeing. How many people are actually there? 208. So you might just go in a little bit like I'm doing. There's 208. Remember how I said leaf 3 was the second biggest? There's 155. Remember how I said that leaf 1 and 4 were close in size, 135 and 130 respectively. And that's all those dots right there. How many females were there? And this is a little bit easier of a question, but these are where the tougher questions come into play. Just simply, how many females were there? And I'll give you help. How many females were there who want to weigh more? How many females were there who want to weigh more? How many females were there who want to weigh more? Dots. How many females were there who want to weigh more? How many females are there who want to weigh more? How many females are there who want to weigh more? The females are in leaves what and what? 41? Oh, so the question is, are you satisfied with your weight? No, I wish I weighed less. No, I wish I weighed more. And yes. In leaf 2, let's take a look at leaf 2, right? Leaf 2 is the one I've already highlighted in yellow, which is this. So leaf 2 is the following. There are 41 females in leaf 2 who are satisfied with their weight. No, Blanca, 100 points. This is practice. Blanca, thank you so much. So there are 41 females in that leaf who want to weigh more. I mean, who are satisfied with their weight. Oh my gosh, who are satisfied with their weight. Where are the females? Let's slow it down a little bit so I might get the right answer in a second. Where are the females? Where are the females at? Explain to me where the females are at. I'll give you hints. Where are the females at? Where are the females at? Where are the females at? The females are where? Just tell me where they're at right now. Where are all the females? They're all in blank blank. Leaf 1 and leaf 2. Okay. So we know that the females are in leaf 1, leaf 2. Let's go shade this on this output. Now, slow it down. You got this. You got this. Now can you tell me how many females want to weigh more? Just these are all females. Everyone we have right here. Do you see this portion right here where it says gender female? Everyone here is female. How many females want to weigh more? They said, no, I am not satisfied with my weight. I want to weigh more. 2. Does that make sense? Good practice right here. Good practice. More chill music. Good practice. 2. 2. Now I'm going to ask you the tougher question. What percent of females want to weigh more? This is the tougher question. What percent of females want to weigh more? Now I'm going to zoom out here a little bit because there's a help on the screen. I'm going to put the help so you can see it. What percent of females want to weigh more? I'm pausing on this question. So then the question is, the first question was, how many females want to weigh more? And we got that by just this number right here. That's how many females want to weigh more. There was 2 females, because this is all the females. And now I want to know what percent of females want to weigh more. So I've got a hint over there on the far side of the screen. That might be right, Marjorie. Marjorie, good work right there. Show me the mathematics. Marjorie might be right. So the first question you want to ask yourself is how many females? Great job. Yep. You saw the hint over there on the side of the screen. The first question you want to ask yourself is how many females are there? There are a total of 343 females. Does that make sense? Like the total amount of females is 343. And then 2 out of, because we've shown all these people are female right here. No, that's all right. That's good practice. Good practice. 100 points. Good practice right there. So 2 out of the 343 people who are female want to weigh more. Now contrast out the males, and this might be easier to do now. So we just found out only 0.58% of females want to weigh more. Almost like 1 out of 100 or 1 out of 200 almost. What percent of males want to weigh more? What percent of males are like, I'd really like to weigh more? So go over here to the male portion and ask for the males. What percent of those males want to weigh more? So this is good practice. What percent of the males want to weigh more? See, because this is where we speed things up and we get a little bit better at the practice. What percent of those males want to weigh more? And we're going to do weapon of attraction next. So we got here all the males. So what percent of the males? Is it 15.8? It might be. It might be. Oh, no, it's not? So we need to figure out how many males want to weigh more. First off, Marjorie's got how many males want to weigh more, and I think someone's already solved it. Great job, Olivia and Bridget. You are correct. The first question would be how many males want to weigh more? We have identified that leafs 3 and 4 are where the males are at. Please note this graphic right here. That's where the males are at. It's also noted down here that leaves 3 and 4 respectively has the males. You see how we've marked our screen to make sure we can see where the males are at. So there are 55 males. The next question is what? 55 males. We need to know. Tell me, fill in Brian's blank. Now that we know 55 males want to weigh more, we'd also need to know what, which is this number here. We know there's 55 males who want to weigh more, so we want to know what percent of males want to weigh more, so we need to know what does this number mean right here? Like, people might see this number, but then what does 285 mean? Well, we know we have 55 males who want to weigh more. 285 is the what? Hence why we're going to do this right here. We're going to do 55 over 285. The total amount of males, exactly. So that's the percent. This would be the percent right here. It's just good practice to know what the numbers mean and why you're getting them, because you can solve a problem one time and be like, I solved it. But if you know how to solve it, you won't get stuck on the test. So we're here to learn how to solve the problems, not just get an answer one time. So that is the amount of males. There's 55 males who wish they weighed more. That would be literally these dots in here. Dots. These are the males who want to weigh more. And then we would need the total amount of males, which is all of this right here. So that's looks like about 20%. Yep. There you go. And that would be this right here. Those are those males. That's about 20% of the males. Cool stuff. Let's do that weapon of attraction one. I am very interested in that. Let's see what decides how people choose their weapon of attraction. Do you use humor, looks, or what is the last one? There's humor, looks, and something else. So we're going to put satisfy with weight down here in the X's again. And then we're going to do this. We'll do one more tree after this because we've got to do a quantitative tree. Where's weapon of attraction? Here it is right here. Let's find out the number one thing. I put EpiPen on the computer. I might use it one of these days. The number one thing, or the best way that people attract a mate, is going to be how attractive you think you are. And what do you think people who think they're attractive might be more likely to use? Just take a wild guess right here. I have a question. Instead of 2, because there's multiple groups. Good question. There's multiple groups. So since there's 4 groups right here, we have 4 colors. And what do you notice? People who say they are more attractive are more likely to use their what? People who are like, I am so attractive, they were more likely to do what? Does that make sense? These are the people who say, my attractiveness is in the top quarter of attractiveness. I use my looks, of course. You sure it is? You sure? Next split right here is how smart you think you are. This is so cool. And when people think they're smart, I mean, do you think you're smart? Yeah, I use my intelligence to attract people. I think I'm smart. Oh, we got a symmetric cool drink. Oh, this is so... These are people who think they're attractive and they like to drink. Okay, let's go look at this leaf report. I love this. This is amazing. Okay, so down here at the bottom, it's a much bigger leaf report, but leaf 1 right here are people who think they're attractive and they like to drink, and a vast majority of them are using their looks. 27 out of the 41 people, which is well over 50%. If you think you're attractive and you like to drink, you're all about those looks right there. Where, you know, we might split it one more time, see what we get. This is also a looks. That's boring. We already did looks. Let's split this one right here. You can choose where to split. That's kind of the end of the tree, and we do get an R squared of only 6.6%. 6.6% of the variation in what people use to attract someone is based on the variables in the tree. 6.6% of the variation in the Y variable is explained by the variables in the tree. Not too much, not too great of a tree, but a lot of fun right there. Let's go over one more tree right here, and we've talked about a lot of these ideas right here. And let's do one more tree. What variable are we going to predict? Help me out here, chat. Tell me what variable we're going to do. We need a quantitative variable, because trees can do quantitative x's, quantitative category y's, anything. Just not those indicators. Identifiers, or things that act like identifiers. So what are we going to do? What variable are we going to pick? Tell me a variable. Tell me the x number on it too. What variable are we going to predict? We might not get a good tree with it. We'll find out what we get. We'll do it a little bit quicker. What variable are we going to do? Books. Which one is that? Books read a month is 26. Let's go do it. Let's see why people read. Well, we're going to remove the coloring right here because this is a quantitative tree. So we don't want the colors on there because it's not categorical. Number one variable on reading books is how many Harry Potter books have you read? Obviously, if you read more Harry Potters, then you will always in shower length. So we'll do that one next real quick. Your favorite alcohol. These are our mega readers right over here. They're going to read a bunch. And can we split them? Fastest car speed is actually improperly coded. That's not an identifier. It looked like one, but it was because of that. People who read the most read more Harry Potter and have less Facebook friends. These are the means for each of the group. There are 37 people in this group who report that they have read greater than or equal to 7 Harry Potter books, which I think is all of them, right? Is there 7 Harry Potter books? And we have right here, they have less than 275 Facebook friends. I don't even use Facebook anymore. Let's go over here. Read to relaunch. People said 26 or shower length. Oh, 26 is books read a month. We already did that one. And then shower length is where? Let's see if that one actually comes out with something. Shower length, 27. Okay. Do we get anything interesting with this one? Let's find out. Number one variable is gender. There you go. Number one variable on predicting shower length, which explains almost 10% of the variation is gender. So there you go, some differences there. And your hair color. What? Wow. That actually jumped it up a bit. Why is hair color playing a role in that? It's interesting. And GPA next. We might be towards the end of the tree because we're not seeing a big increase in R squared. But there you go. Hair color and gender, the best 2 variables. And let's look at the split history. Split history shows us the increase to R squared after each split. You generally stop when you see less of an increase. So we're looking here at the percent of variation explained. I don't know. When do we stop the tree? No one knows. There's a way to tell. We get into it in other classes. But we want to see how much of the variation can be explained by, other variables. And look at this difference right here. Females compared to males spend about how much longer in the shower. The difference right here between the means of the group is about 4, where you see 285 males had an average shower length of 11.6. And also notice that you do have somebody, this is ridiculous. Please tell me about this individual. I mean, I'm not a judgy type person, but I'm like, this is how long you usually spend in the shower. I'm like, really? Really? The brown hair. You in this group right here. And then, so yeah. No, like this right here, this person, I'm like, they're napping. They's like, I take my nap in the shower. That's what's going on right there. I have no idea, but that's a bit ridiculous. If you ask me. If that's like your, well, on the other end of the spectrum, you got down here. This is like your average shower length. Is that like 3 minutes? Go find out. Go to table subset. I want to see this. I want to just see what they said. They said their average shower length is 3 minutes. Sure. From a concert. Oh, that's craziness. That's what I call efficiency. When your man is annoying, you do what you need. Facts of life right there. Let's over to the main screen. Okay. Next topic. Getting some practice done. Chilling out before the Kahoot. Let's get the next topic up and going, which is Chapter 10, Sample Surveys. Cool. We're about to some Chapter 13. Uh-oh. Chapter 10, Sample Surveys. We need to do some definitions right here. Chapter 10, Sample Surveys. I can't clean my room, Mom and Dad. I gotta take a shower. It's gonna take the rest of the evening. Let's do this. But fun is bad, so Chapter 10 is good, right? So... Populations and samples. Well, who's got a little saying for me to help me out with this right here so we can keep these straight? Who knows our saying right here to keep straight population parameters and sample statistics? And let's talk about what these are. Who's got a saying to help me remember population parameters and sample statistics? And I'll talk about them here while you remember that saying. What we need to talk about is a population parameter is something we want to understand. Population parameter. What we want to understand about a group. Like the group is the population. PPSS right there, population parameter, sample statistics. Great job, 100 points in the chat. Ian, good to see you here. And so we want to understand what we want to understand about a group. So when you think about this, like if we're going out to Knoxville, and we're looking at the roads in Knoxville, and we want to measure the amount of potholes in the road, the amount of potholes, the true amount of potholes that exist in the roads in Knoxville would be the what? Like the roads are the population. We want to understand the roads. The roads would be the population. So we want to understand roads. So the amount of potholes that exist, like per mile, like we're saying like Knoxville has an average amount of potholes per mile of this. Hopefully not that bad. Tennessee roads are good. I like Tennessee roads. Take me home. So the amount of potholes per mile, which could be something we measure, is the parameter. Now this is the truth, right? So we want to understand the amount of potholes per mile on Knoxville roads. Like this is the truth that exists, like an actual truth that exists. But then we could go out and collect a what? Like we could go out to try to figure this out. Our estimate taken from a sample of data. Going out, taking 100 miles of roads, and calculating the average potholes per mile. So this is not the truth. The statistic always gives you a what of the truth. So whenever you have a statistic, it'll always give you a what of the truth. The statistics, I'll go average. Statistics. The statistics will always give you a what of the truth. So you always use a statistic because you're saying, well, I'm going to go out and take some samples right here, take 100 miles of road, try to figure out what's going on with this. It's always going to give you an estimate. Bridget, great job right there. It's always going to give you an estimate of the truth. So we use this up here to estimate this quantity. Now, we'll be talking about another way of doing it here later on. But so when we get a statistic, we're saying, let's go out and collect data on the roads to see if there's anything wrong with the roads. This will let us get a better understanding. If you knew everything right now, could you know how many potholes there are per mile in Knoxville? If you knew everything at this moment, would you know that? Yes or no? Like, would you know this? Like, if you knew everything, you're omni-knowledgeable, omnipotent, omni-something. You're all omni. So if you knew everything, you would know this. But we don't have that ability a lot of times. We can't know everything. So what do? We go out and take samples to get estimates. Ian, right there on track. You got it, Ian. We don't have these abilities. We don't have the ability to know how many potholes there are per mile. So we go out and take a sample to estimate how many potholes there are per mile. And then we can see if there's a problem. If there's a problem, we'll go out and fix it. Like, you're like, well, we need to get some more money because there looks to be a problem because we estimate from the samples that the population is a problem. We don't know the truth of the population. We can only know the truth for a sample a lot of time. Well, sometimes you do, chapter 13. Sometimes you do know the truth. So when we're doing this right here, there's another key term we need to know, and we have such thing as the sampling frame. Now, the sampling frame is going to be what? Everything we have access to what? When we talk about a sampling frame down here, and these are definitions you should know, sampling frame, everything we have access to sample. It's not what we sample. This sampling frame is not what we sample. Those would be things that are in the sampling frame, though. Like, you can only sample things you have access to sample. So the sampling frame is anything you could possibly sample. So let's say there's some private roads in Knoxville that they won't let us travel on. What would you say about those roads right here? If there's private roads in Knoxville that we're concerned about all the roads in Knoxville, and we want to know like how many potholes there are, but there's private roads, like let's say, is Oak Ridge in Knoxville? No, Oak Ridge is like Oak Ridge, right? Let's say there's like some Y12 owned roads or something like that in Knoxville, and they won't let us travel on them. So they will not let us go on those roads. Now, we want to know how many potholes there are per road per mile in Knoxville. So now, it's kind of, it's Oak Ridge, right? So we actually want to know about those roads. Exactly, so we can't sample them. One of my favorite questions to ask to make this very clear is, we go to, you're going to hear the same questions, to the library at 2 a.m. to talk to students about study habits. We ask them how many times a semester they go to the library. Identify the following. Population. Let's try to do this right here. This is your practice. Sample. Parameter. Statistic. Sample frame. Identify all those right here. Can you do it? Can you do it? Let's start out right here. A little bit of music. Try to do it. Very kind of simple, short question. I know it might be like, well, maybe are we talking about what? We're talking about what? But try to do it here. Population's all students right there. Bridge, a great answer. All students. I think it's fair enough. We want to understand students. Question makes that clear. UT students, maybe. You could narrow down like all UT students. I'm fine with that too. Good deal. What else we got? Careful. The sample is going to be what? This is why I do the practice right here. So I'm glad I did this example right here. The sample is going to be students who talk to us and give us data. Whoever we get data from is going to be the sample. Like, when you sample something, you get data from it. Does that make sense? Like, your sample is the things that give you data. So if you talk to someone and they give you information, they're part of your sample. But the sample frame would be all students who what? Who do we have access to talk to right now? Think about what the sample frame means. The sample frame is anyone we have access to talk to. So think about who we have access to talk to. This is your sample frame. It means anyone you could talk to, theoretically speaking. Students that, yep. Which might not be representative of all students. So the sample frame is more theoretical. That's where people usually get a mistake from, is they say, and we might want to put the sample frame in between these. Usually these go down in size because you can't have a sample that's bigger than your sample frame. And what happens if these are all the same in size? Like, what if we were interested in everyone, we have access to everybody, and we talk to everybody? What would we call that? If these are all the same size, like we're interested in all UT students, and we have access to all UC students, so we talk to all UT students. Like, if this theoretically happened right here, what would we call this? Like, we have access to all UT students, and then we get data from all UT students. At this point, which is a different question, we call this a census right here. That's called a census. When you take data on everything, great job, Bridget, just amazing work right there. When you take data on everything in the population, it's called a census. Like the US Census is trying to get data on everyone in the US. This is now a census. Let's make that very clear right here. Once again, this is practice, so make sure to write these things down, that a census is when you take data on everything in the population. It's like a census, it covers everything. Can anyone identify? Undo. Oh my gosh. Can anyone identify the parameter of interest? The parameter of interest would be what? The parameter of interest is what's the truth for the population. So this is where it gets a little bit complex, and I think usually people struggle with these types of questions, like what is the parameter of interest? The parameter of interest would be the true average hours all UT students go to the library. But now think what the statistic would be. The statistic is going to be what? And this is what we want to know. We want to know the true average hours that students go to the library, all UT students. So now the statistic, which is our estimate of the truth, which is probably going to be biased. I do agree. This is not representative. The statistic right here is going to be what? Just use this because that's what we want to understand. This is what we're going to use to estimate it down here. What is the what? What would be the statistic? The statistic is going to be what? The statistic, which is used. Ian, you're on the right track right there. It's going to be from our sample, the average hours they go to the library. So this is from our sample. Notice how it comes from the sample, or you could say the population, or the population average hours all UT. So for all, because we say all UT students, the average hours in the library per semester from our sample. So the statistic is when we talk to the students and we say in the library, like, how many hours do you go to library? That comes from our sample. But then we're trying to use that to estimate the truth for all people. Does that make sense? The way these are distinguished? This would come from the sample, and it's thus a statistic. This would be for the population, which is the truth for all people, and thus we'd call it a parameter. So once again, the statistic is an estimate of the population. The statistic comes from a sample where the parameter is the truth for the population. It's just like the graduated version, like parameter is the advanced version of statistics. Definitely chapter 10 homework. Chapter 10 homework. So, and flashcards are good for this chapter. Flashcards are your best friend for this chapter. This is chapter 10. Let's see here. We got a few more things to talk about. We have these different types. So let's do bias first. So when it comes to bias, we have different types of bias. And the different types of bias are response bias. When the bias is in the response, people give questions that might make you want to answer a certain way. Do you think it's fair that the drinking age is 21, but you are in college on your own? Maybe, I think drinking and tobacco right now are both 21, right? So you can be like, I can drive my car, go get married to someone, and go buy a house. And I say, well, I'd like to buy a beer. Not happening. Do you think that's fair? What I'm putting in here is some response bias by asking, do you think it's fair, and giving a preference. The question should simply ask, should the drinking age be 21? Remember, the best way to remember this is that response bias is when the bias is in the response. You're pushing people to answer a certain way. What's another type of bias? Who can remind me of the other ones? They were on the screen just a second ago. There should be at least two others. I might include another one here. But what's another type of bias that we have that, like, let's say we don't talk to enough people from a certain group. We might what those people. What's another? Voluntary? Yeah, voluntary. Let's do voluntary. Good job, voluntary. Voluntary bias is when people who volunteer might have stronger views than those who don't. So you can think about things, like any sort of survey you do where you're trying to get people to respond, and people are like, oh yeah, I'd love to take your basketball survey. Well, if you're asking people like, how many hours of basketball do you watch a night? Well, if they want to take a basketball survey, they probably watch basketball. So if you're asking UT students and the like of how much they like basketball, probably not going to get a good view of that. The other one right here, under coverage. I always like to do political ones for this. Under coverage. You go to the college what's Republican or Democrats. I'm gonna write the definition here. Someone put Republicans or Democrats in the chat, so I don't pick it. You pick it. Under coverage right here, and we say when you don't have enough of one group in your sample or too much of another. A tricky way to ask this is when you overcover a group, because overcoverage means undercoverage of another group. So I might have to do my coin next to me. Oh, I got my coin. It's heads, it's Republican, tails, Democrats. It fell. It was tails. Heads, Republican, tails, Democrats. Okay, you go to the college Democrats, and you say the college Democrats, what are your views on Biden? And they're like, oh, I don't know. They say you get a lot of goods because Biden's Democrat. So you might be more likely to get good right there. So if someone said, well, is this representative of UT students? You'd say, no, you went to just the college Democrats. Now, it's not a problem by going to that group, but you're undercovering other viewpoints. You have to have a good representative coverage of viewpoints to then put the results onto a population. So you can't just go to one group. You need to make sure you have representation for your survey on whatever group you're trying to do. The other ones are going to be non-response. Got some non-response right here. And then we'll do convenience next, which I can never spell. Non-response is when people who don't respond differ in the views than those who do respond. So non-response, generally, if people don't want to answer your questions, they might be offended in some way. It's possible. And thus, if you have people who just have certain viewpoints and don't want to talk about them, that's a bit of an issue when you're trying to understand viewpoints. Next, we have convenience. Convenience, is this semester? No, it's never going to be this semester. I never know how to spell that word. Convenience right here is going to be basically getting the easiest people to talk to. So talking to the first or easiest people, putting something online. Great way of doing it right there. But convenience is never going to be really representative of a population if you just go and talk to the first people you have access to. So now we get into the sampling methods. What should you be doing right now with these if you have not done it already? What should you be doing? What is this chapter all about? What do you need for this chapter? And I can't state this enough. If you haven't done this with this, you need to get out some note cards right now. Jacqueline knows right there. Jacqueline's points for you right there. What's between non-response and voluntary? Non-response is like I go out to Ped Walkway and I say to people, I hold up a sign and I say, it's a little bit like voluntary, right? Non-response speaks more to the people who choose not to speak to you. So it's almost like Nicole, great question right there. Voluntary is more about people being excited to take your survey. It's maybe more like you've got a lot of people jumping to take your survey, so they're kind of going to be, your survey is going to fill with a bunch of people who, like, you only have so much time to sample so many people. So when you do have voluntary bias, there's a bunch of people who really want to take your survey. It's not that people don't want to take your survey, but people are like, oh, basketball survey, I'm right there for you. I'll be one of your 100 participants in that basketball survey. But then you have a political survey and people are like, you go and you select 100 people and then 20 of your people who you've selected randomly, like you get a pool of 100 people and 20 of the people say, I really don't feel comfortable taking your survey. I was looking over the questions and I don't want to take it. So now you have people like dropping out. It's not that the people were really jumping to take your survey, which is more of a voluntary bias. Non-response, they're going to like start doing it and be like, I don't want to do this. And so it's not really that, like, once again, people are like, oh, I want to take your survey. It's that people start to take it and they're like, no, I don't want to take this survey. But they're kind of opposites of each other. Do these change if you often are incented to take the survey? Yeah, that can cause an issue. Are there different variables? Incentives might create voluntary bias. I would say an incentive might be connected to a voluntary bias because people who like the incentive are more likely to take it. So you have a little bit of an issue of people who might be attracted to take your survey. These can go by other names in other disciplines too. Like sometimes called like the good, well, that's when someone wants to agree with you, the good participant or good subject effect. Some people take your survey and they're like, ooh, what are you researching? Oh, I'll help you out. What's your kind of goal for this? And you're like, that's not the goal. It's supposed to be you. Sampling is one of the hardest things to do. Like doing research, not fun. Fun, bad. Research, fun, bad. Great questions, right? Keep asking those questions. This, once again, this is the kind of simple version of it, but these questions get a lot more complex. Are there any last questions on this? I just want to pause because we got to make sure we got like 2 more big chapters. Any last questions on these right here? If you have a last question, throw it out there. Great questions so far. Let's hop down here to sampling methods. We've got 4 sampling methods. No, we got 4, and then the multi-stage. Simple random sample. Let's write down the steps for this for a simple random sample. 1, do what? Give everything what? Give everything what in a simple random sample. We write down the steps right here so we can remember how to do it, and you should look for these key steps whenever you look at a question to see if it follows them or follows closely to them. The first step for a simple random sample is to give everything a what? Give everything a what? Pretty much, Blanca, that is correct what simple random sample does. It gives everything an equal likely chance to be selected. Everything gets a number. And then numbers are selected randomly. And Blanca right there, and also Kayla, excellent work. 100 points out there. So everything has an equal and likely chance of being selected right here. Just think of like putting ping pong balls into a big jar and drawing one out. They all have the same equal and likely chance. Next we have right here is systematic. Systematic sampling is going to be, first off, start at a random point. Go to the library at 4 a.m. Pick a random starting point. Sample every kth observation. So explain to me, Brian's going to go to the library at 4 a.m. Picked out a random time right here. Random time. So Brian's going to go to the library at 4 a.m. and talk to every what individual? Kth is just a placeholder for how much you want to space it out. There is more theory, like if you're doing a certain, ask every kth person exactly. I'm gonna watch people go to the library and say 1, 2, 3, 4, 5. I'm gonna talk to every 5th person who goes in the library. So this kind of does a systematic spacing out of who you're talking to. Now here's where people get confused. Where confusion begins. Those are the easy ones. Here's where confusion starts. Confusion usually starts here when we get to stratified. Stratified. There we go. Stratified. Got it. Now, stratified. Start by doing what? Great job, Blanca, right there. Start by doing the what between the groups. Who's got their notes? You'll hear me say all the answers, but it's good to practice. So we start stratifying by doing what between the groups? Careful. Check your notes. Don't cry. We got this. We're going to take a stratified sample. Acknowledge a difference right there. Nicole, excellent work. Some points in the chat. Start by acknowledging a difference between the groups. We'll talk about how to do this here in a second. Next, sample percentages according to this difference randomly. We'll say randomly sample. Okay, so what's this all mean? What does this all mean? So this is where we acknowledge a difference. What you're saying here is maybe students who are on campus versus off campus have different views on parking. Would you agree with me? Like, if you're on campus or off campus, your views on parking may differ. Like, if I were to talk to only on-campus students, that would not be representative of parking, like what UT students think of parking. Or if I were to talk to only off-campus students, that would not be representative of what students think of parking. Like, you better make sure you have a certain amount of on-campus and off-campus students. I'm acknowledging a difference here to start, that the views on parking are going to differ between on-campus and off-campus students. So if I told you, great job, Jacqueline, right there. Thanks for following along. If I told you that UT, I hate those crayons. Oh, don't you do that to me. If I told you UT is 40% on campus and 60% off campus, I'm acknowledging a difference that I think this plays a role in what I'm interested in. And I want to talk to 200 students. How many off-campus students am I going to talk to? I'm going to talk to 200 students. My sample size for my research project is going to be n equals to 200. And so then I'm acknowledging a difference here that I really think there's a difference between on-campus and off-campus students. So I need to make sure I know from the registrar that 40% are on campus and 60% are off campus. So my sample sizes within these will be what? My sample sizes within these will be what now? My sample sizes within these will be what now? This is what stratifying means. How many on-campus students will I speak to? And why? Because I'm acknowledging a difference and saying there is a difference between on-campus and off-campus students. So since there is a difference, I'm going to sample a certain amount of on-campus, I'm going to sample a certain amount of off-campus to be representative and not undercover certain groups. So the amount of on-campus students I will talk to from this group is how many? 80 on-campus, Jacqueline, great work right there. And then the sample size for this one is going to be 120. So you always acknowledge a difference between the groups. You always acknowledge a difference with stratified. Now, really? Okay, you want to be that way. Now we go here and we go to, there we go. Now we go to cluster. That's where the confusion starts. Cluster is also about groups. But when you have cluster, things are what into groups. When you have clusters, all your groups have been what assigned. Clusters start off with groups that have been what assigned, or should be, theoretically speaking. It's a big assumption that the groups have been assigned this way. Give you a hint. Random. It's not random if you're on or off campus. That's not random. Groups are randomly assigned. Whole groups are selected to sample. Census performed on each group. If we did a census right here, we would speak to how many of these on-campus students. Like if this was some sort of clustering scheme, and we did, which we're not doing a census right here. If we were to do this as a cluster scheme, then if we did a census, how many of the on-campus students would we speak to if these were clusters, which they're not. But what you would have to see, it says at the end of the problem, we speak to how many on-campus students. Every on-campus student. So if these were clusters, which they're not, at the end of it, it would say something like we speak to all on-campus students. No, we're speaking to 80 on-campus students because we're being representative of the differences between the groups. So if it was clusters, it would say speak to all on-campus students. But what about this? If we were to go, and let's say UT wants to understand, let's say, UT wants to understand the views of dining. So they go to the student union and speak to 50 tables of students. What are they assuming about each table of students? Which is, I know it's not true, but it's an assumption that we start out with. What are they assuming about each table of students? And this is where we would be doing a cluster. They're assuming what for each table of students? Got to go quicker with the next chapter. They're assuming what for each table of students? Well, we will assume, good job, Ashley, right there. They're assuming that each table of students is just a random group of students. That they're just a random table of students. Does that make sense? So they're assuming that a table of students is just a random group of students. So then they're going to select 50 tables right here. And then they're going to speak to how many students at this table. They're going to walk up to a table of students and say, hi, we're here to ask you a survey. And there's 8 of you at this table right here. And we just wanted to talk to you about this survey. They're going to do what when they go to a table of students? Each one of these tables will be a what of students. Just think each table is a what of students. They're just walking up to a table and saying, hi, we're here to talk to you. We need to speak to, just if you could fill out this survey, we'll give you a $5 gift card. I'm here with UT Dining. You can see my Airmark shirt on. So I need to speak to all of you. And I'm going to talk to everyone at the table and hand them all a thing they should fill out. And I'll just pick the pack up. Does that make sense how it's doing a cluster sample right here? I've never done what by talking about tables of students. I have never done what by saying tables of students. I'm just saying, let's go to a table of students, another table of students, another table of students, another table. We want to understand students. So let's just go to table of students. I've never done what, which is a key thing up here. I've never done this. It's just another table of students, another table of hopefully random students. Just go to another table. I've never done this. So we're just going to go to table. And what have I not done from stratified for the students? Like you never hear me say this. I've never talked about a difference. It's just another table of students, another table of students, another one. Does that make difference? Does that make sense what these differences are? Whenever you hear stratified, there will be a difference to start. Whenever you hear clusters, it's about taking a whole bunch at once. If I were to talk about donuts, let's check this out. Donuts. Which of these is how we stratify donuts? Is a dozen donuts a stratifying of donuts, or is glazed versus filled donuts? Which one of these is the strata, and which one of these is the clustering of donuts? Which one of these is the strata, or which one of these is the clustering? So which one of these, explain to me right here. A little more review on this, then we're going to hop to the next topic. Oh, thank you, Ashley. I'm so glad. I'm so glad. Which one of these is the strata? Which one of these is the cluster? Strata is the, yeah, it's literally the verses. If I write verses, it's because that's the difference. And dozen is a cluster. It's just a whole bunch of donuts. Here's a dozen donuts. I didn't tell you any differences. It's just a bunch of donuts. So if you were to say something like, here's where you help me out. If we were to say something here about like soda, when would we be doing a cluster of soda? When would we be doing stratification of soda? So now I want you to help me out with this example and do like a reverse where I tell you, how do we cluster soda? And then how would you stratify soda? Like if you were to take a cluster sample of soda, you would just take a what? I think, Kelly, you are right. Go a little more in depth on the cluster though. Coke versus Sprite is going to be, or Coke versus Pepsi, Sprite, whatever you want. Coke versus Sprite, we're to examine that, or diet versus like regular. Like maybe we're working at a factory and we want to examine the difference of diet versus regular. So that's going to be stratification. And then when we do a cluster, it wouldn't be like all Coke products. A cluster would be taking a whole bunch at once. Ashley, good practice right there. Ashley, 100 points. And thank you so much. Everyone practicing along right here. We're not going to take all soda at once. The clusters would be what though? So that's where the clusters would be what? If we go into the factory and we take clusters of soda, we're probably taking what's of soda. Let's go take some cluster samples of sodas. So we go into the Coke factory here. Packs right there, you got it. So 12 packs. Does that make sense? We could sample 12 cans at once by taking a 12 pack, and that's a cluster. Does that make sense right there? A cluster is going to be like taking a 12 pack, because how many samples do we get at once with the 12 pack? Jacqueline, great job right there. So, and this is the practice. Like we're taking a whole bunch at once. I never told you any difference. I never said diet versus regular, Coke versus Sprite. That's going to be like a stratification right there. So if we were to go to students, well, we already do students. What is another one? I'm trying to think. I've got so many different examples with food because I'm all about that food. Let's go. I think what we're going to do, we'll hop back to the main screen. I've only got so much time. I already played that one. Like nephew Tolliver. He's like, Uncle Brian, we already played that video game. I'm like, I'm sorry, Tolliver. All right. I'm going to drop this in the chat right here. So we got 32 people watching. Thank you for sharing your Sunday right now with me. 32 people watching right here. More food. I'm going to grab a little bit of food between this. So I'm probably going to take like a 10, 15 minute break. So we got another 25, 30 minutes. So let me drop this in the chat. This probability lecture here, which has 342 views. Thank you so much, which is now labeled. Thank you so much. So if you're watching this right now, let me point out, because we go through this, and this is a public video, so anyone can watch this. Or up to the main screen. So this is the review right here. We go through all the rules and we do examples. You're going to get more practice out of this and the other videos than we could in a 20, 25 minute section right here. Here's where we start going over the rules. You can tell which rules are simple and you can tell which rules are more difficult by how long it takes me to go through like the addition versus the multiplication rule. And then we do some examples right here where we list out probabilities. But one thing I do want to point out right here is this table, which hopefully you can read my handwriting. Or Brian, you need a shave, man. What you doing, man? Look professional. Come on. Don't wear some Rick and Morty. Oh, I'm wearing Rick and Morty today. God, look out of it. Is there a chapter? Yep. People have been putting that in the chat. We can find it for you if you need be. Message me on the Discord if you haven't, and we can find a lot of videos. So I go through here and write out the full table and explain it. But check out this video right here. Will we have any questions that you find a number on the normal distribution? You could have to find like a z-score. Let's start doing some of that here. But check out this video if you haven't. We go through here and we explain how to do all this. The rules right here, the complement, the addition rule, and the multiplication rule. And Brian eventually will shave. But check this out. This is a great review. And thank you to everyone who's watched this. 51 downvotes. Go and downvote that video now. Trying to make it the most disliked video on the channel. Oh yeah, let's go back here to the main screen. Let's do some chapter 13. Chapter 13. Okay, and we will have more of those questions tonight from probability. We've got a really good review over that, and with our limited time right now, we're hopping to some chapter 13. Whoo! What do people think of chapter 13? We're about to get serious right here with chapter 13. Ooh, chapter 13. Ooh, and 14. Whew. Let's go check this out. We're going to try to spend like 15 minutes. I got a timer. No fun. No bueno. 30-minute timer. I got 10-minute timer. Okay, 10-minute timer started. Let's try to do this here. Okay, here we go. Chapter 13. Let's get this going. You hate it? No! Good job. That's what you're here for. Notation, notation, notation. You see a lot of notation throughout all of this. Let's identify some of the notation and learn how to do this. We've got here p hat, we've got here p, and we've got here n. Now, these are actually connected to what we just were talking about, where p is a population parameter. Check out the last part of this video. And p hat is a sample statistic. Now, in this chapter, we know the truth. Imagine you're at the registrar. Do you think the registrar knows what % of students are in state? Yes or no in the chat as I write out this question. So that's what you got to tell me. Do you think the registrar knows what % of students are in state for University of Tennessee? So we want to sample 200 UT students and ask them if they are in state or out of state. The registrar reports to us that that 70% of UT students are in state. What is the sampling distribution? And what would be unexpectedly high? As in more than 2 standard deviations above the mean. Okay. Full question written out right here. You are correct. The registrar would know that truth about what % of students are in state. And I don't know if this is the truth. I like do you guys like the chill music? I like playing a little chill music in the background. Like, I don't know. It gets me like chill too. So first things we need to do is identify what's going on right here. This question right here has a lot to it. First thing you should notice is you have some sample size stuff. Sample size is n. So now we have the sample size right here. Also, we have this value highlighted in blue. The registrar knows the truth. Oh, thank you, Ian, right there. So what is that value in notation? If the registrar knows that, helps me distress too. If the registrar knows this, then what of those notations up there is it? I've got my notation kind of marked. I need to know the difference between a population and a sample. So what is this right here in notation? So the registrar is reporting to us. Registrar, you got it, Blanca. That is P. That is the truth. So that is the truth for a population right there. That is P. So then we're asking, if we know 70% of the population is in state, what could theoretically happen in a sample? And now this gets a little bit confusing because the equation looks complicated. And that's where we're getting down to know the mean and the standard deviation portion. Does anyone know the equation to find what we would expect? That means expected or mean in a sample proportion. What do you expect to see if you take a sample? That's how that reads. Great job right there. Charlie, good practice. Charlie, some 50 points in the chat. What do I expect to see in a sample proportion if I go out and take a sample of 200 students? The expected sample proportion, that says expected sample proportion is what? The expected sample proportion is going to be what? Well, if 70% of the students are in state, and if I take a sample, I'd expect in a sample mu p hat equals mu. It might sound a lot, but you're just saying UT tells me 70% of the students are in state. Well, if I take a sample, well, then I expect 70% in state. People are also identifying immediately that if P is equal to 0.70, then Q is equal to 0.30. Please notice this question is categorical. That's where usually mistakes are made. I have a big video also in the review. Where's that review thing? Mubot, help us out here. But I've got a big video going over the difference between these. I'll show that here at the end of this problem. But this one right here is going to be P's and Q's because it's categorical. Oh, no worries, Blanca, you got this. So now we're doing the standard deviation, which a lot of people are solving for. And this is, once again, 1 minus P right there. Please ask if you're stuck on it. This is the standard deviation of the distribution. And that's the standard deviation for what we might see in a sample, which is the variation is going to be P times Q over N square root. P times Q over N square root. So mu P hat, where are you on mu? Mu P hat equals to 70%. And then the standard deviation of p hat. Gotta start blocking that. Nice job. Thank you so much. Positivity right there. Everyone being positive, helping each other out. Love it. Has anyone solved this for me yet? That's 21% over 200. So you take half of that. Oh, I'm not doing that in my head. Right over there. Who's got it? No one got it yet? Oh no, that means I gotta solve it. 0.7 times 0.3, 200 p times q over n square root. 0.032. It's off the screen. 0.032. So now that we have the standard deviation and the mean, what can we draw for this distribution? Now that we have the mean and the standard deviation, what could we do? We can draw it. The mean goes where the mean is at. Standard deviation is kind of a distance or a spread of the distribution. And so the mean is going to go here at 0.7. Oh, no worries. You got this. What's for dinner, Kayla? I'm just going up a standard deviation. I'll draw it visually here in a second. And there we go. So this is the standard deviation. And that's how much we're going up each time. This is the mean of the distribution. Great job, normal curve, you bet. And so guess what? We just answered the question. This would be the percent, or we can find out how many there are. Regression for categorical, so we can, wait a minute, I think maybe we got the test coming up. So yeah, we might do a little bit of review on it. Might do a little bit. So the answer is, what would be unexpectedly high? 76.4%, or if we want to know a number of students, we would just time that 76.4% times 200. And 152.8 students would be unusually high right there. I'm going to grab a little bit of food after this. But this is what would be unusually high. Who knows the conditions right here? And let's check them. Let's check the conditions for Brian's problem that he wrote. So who knows the first condition? You can see it up there. Who knows the first condition? Condition 1 is always what now? Would you didn't see what it was? Oh, shrimp Alfredo with homemade sauce. That sounds amazing. The sampling distribution is a theoretical thing of what could happen if we took samples of students. So the sampling distribution is saying, like, theoretically, what could happen if we took students? Like, we know that right now, 20% or 70% of UT is in state. So here's what could theoretically happen if we took samples. So, and people know condition 1 is random. So got to do it. Obligatory. And so did Brian randomly select these 200 students? Maybe test question will be more clear. We want to randomly sample. Yes. Problem says it. Thank you. They're right there. We've had omelets the last 2 days, and they've been amazing. My fiance is like best omelet maker ever. Like, and people might say that about there, but I promise you, really good stuff. What is the next condition? Who knows the next condition? I say condition 1, random. Condition 2, what? What's the next condition? What is the next condition? Condition 1, random. Condition 2, what's the next ones? I know, right? We got some goat cheese for more omelets. So 10%. Goat cheese is awesome. Goat cheese is definitely S tier. So we have here 10% which says we need to sample what? Now this is where we pause. We'll pause after this one. But we need to sample what? Our sample needs to be what, and did we pass this? So this one should be pretty clear cut if you know the 10% condition. So take a moment, try to explain to me the 10% condition, how you would look at this. So you must identify 2 things with this. So did we pass the 10% condition? Yes or no, and why? Blanca is correct. We need to sample less than 10% of the entire population. Do we pass that? Yes or no, and why? So the things you want to look at right here is, so let's go here. A, what is the size of my sample? B, what is the size of the population? Is my sample less than 10% of the population? What was the size of Brian's sample? You are correct. Brian's sample was 200 UT students. The population of UT students is something like 30,000. So did we sample less than 10% of the population? I would say here, Brian's sample of 200 students is less than 10% of the 30,000 UT students. Does that make sense? What the 10% condition is? Brian's sample of 200 students. Great job, Evan. Evan, everybody, Troop T, good to see you here. You are correct. This is, just make sure to have that down. Look at, it's a lot of steps right there if I state this way, but that's like what you're doing. You're saying, what's the size of my sample? What's the size of my population? Is that less than 10%? Now, the last one people usually get a little bit confused on because it also deals with the number 10. This one for categorical data is success/failure condition right here. And the success-failure condition states that we need, I need to change font size. We need at least 10 successes and at least 10 failures. Now, what does this mean mathematically right here? Oh, I'm throwing 100 points right there. Olivia's got it. Pause. I told you I'd forget every once in a while. Pause is a categorical or quantitative. A lot of people just go through here and take and accidentally do the next condition just by going through by memory. So I'll see a lot of success failure as the third condition just because it's the first one people learn. But this is categorical because we're asking, are you in state or out of state? So the success failure condition is related to the categorical nature of this variable. It's, are you in state, out of state? That's a category. You're in state, you're out of state, that's a category. So we need at least 10 successes, at least 10 failures. So how would we check this? So let's say right here, poise, find n, and then find p and q. Are np and nq both greater or equal to 10? Okay, so what is, people help me out right here. In this problem, what is n? So we need to find n. So n is equal to what right now? What is n? 200. Great job right there. A little more chill music in the background. Great job right there. N is 200. N is 200. I'll put in parentheses. What is p? What is q? P and q. P is the proportion from the population that is in state, and q is the complement of it. So who can solve np and q? So NP and NQ are just multiplying, like you're multiplying these. Who here can solve these and tell me what these are? Go ahead and start solving these for practice and tell me if the condition is passed. Tell me, is the condition passed? What are these? And is the condition passed? What are these? Great job right there, Ashley. And other people getting it too. So is the condition passed? And this will be the other half of it. Condition is passed. These are both greater than or equal to 10. And that's, why do we pass these conditions? What's the whole point of passing these conditions right here? The whole point of passing these conditions is what? To do what? If you pass these conditions, you can do what right here? What's the whole point? I should have checked the conditions earlier on. But the whole point of passing these conditions is to do what? Is that right there? Whole point of passing them. Oh, no worries, Bridget. The whole point of passing these conditions is to do what? To draw the normal curve. If you pass the conditions, you can use the normal techniques and draw the normal curve. Use the normal curve. Great job, everyone, right there. Let's do some chapter 14. Here we go. Remember, this is just one of many reviews. I do want to point out that there are lots of reviews that we have right here, but this is one of many reviews. So it really comes down to repeating things, practicing things where you're like, oh, we passed the conditions, then we can use the normal curve. And the more you practice, the better you get. So let's check out the last topic of the evening before the Kahoot. Gonna grab some food here. You should grab some food too, because we got Kahoot coming up at 7. Oh my gosh, Kahoot time almost here. Oh, I'm so excited. I love seeing who wins the Kahoots. Like, it's so fun. It's so interesting. There's so many competitive students. Let's check out the last topic right here, chapter 14. Here we go. I already played this song. I've already played every song today. Let's do this. Know the difference between a sample and a population. Same sort of thing going on right here. So this chapter and the last one have a big thing in common, is that we're going from a population and asking what could happen in a sample. What is something UT might know about all students? Let's have you make up a question right here, because we're going to go from a population to a sample. We're saying we know the truth for the population, and then we're asking, well, I mean, what might we see in a sample? So we have to know that this is the sample mean, and this is the true mean. So the sample mean is for that, and the true mean. So what is something UT might know about all students? I need something UT knows about all students. It needs to be quantitative, not like in-state, out-of-state. We're doing the same sort of thing where UT knows something, where they have the answer to it. They have to know something for all students. So they have to know all students this. But majors would be categorical. The tuition rate, yes. How much people are paying? Credit hours, yes. GPA, yes. And so this, you are correct there, Ian. Majors is something they would know about all students, but that would be categorical, and that would be the last chapter about the sampling distribution of the sample proportion. So we could say here, let's go here. Ooh, I like the how much students pay. UT reports to us that the average tuition a year is, ooh, I don't know the answer to this. What is like yearly tuition now in state? Like 16, 17,000 yearly? There's like so many variables, right? $5 million. Let's go here. 26,000. This is in-state, out-of-state combined together. Does that make sense? Just about. I don't know. 5 million is a lot of money. I don't know what to say. A lot is a lot. UT reports to the average tuition a year is this. With a standard deviation of $7,000. The distribution is heavily skewed. We talk to 200 UT students and ask them how much they pay. Draw the sampling distribution of the sample mean. Okay. All my sanity. 30 cents. I wish. Okay. So now we get to this question right here. What is the first thing we always do with these questions? What is the first thing we always do? You should know these steps. If you've watched any of my videos on solving any of these problems, you need to know this step right here. First thing you do when you get to these questions is what? First thing we always do. I'm ready to do it. Oh, great job right there, Kayla. So Kayla's, and Ashley, you're close, but here's where and Ashley, thank you so much. This chapter is the sample mean, so there's no more P and Q. No more P and Q for this problem because that is for true proportion and complement of true proportion. So if UT Registrar tells us that this is the mean and this is the standard deviation. Oh no, Ashley, another 50 points. Don't worry. I literally have had people walk up to me and say, there's no P and Q for this problem. And I say, you might be right. And they say, well, how do I solve it? I say, check out the formulas. I can't tell people how to solve stuff because people will sometimes think that there has been errors on our test where you can't solve stuff. You give a lot of tests, you make an error that creates like an question that can't be solved. But so Kayla, I think, listed a lot of the stuff right here. But no, I've literally had people walk up and say, I can't solve this. And I say, double check. And they're like, are you sure? And I'm like, Ian, do you see it now? Why is this question different? Why is this question different right here? Why is this question different right here? Why is this question different? I'll give you a hint. Why is this question different from the last one? Why is this question different from the last one? Because the last one was asking, are you in state or out of state? It's asking about averages, which is going to be quantitative. And the last one was asking, are you in state or out of state? And that would be categorical. That's where we have to decide. And that's where we do the pause at the end right here, and we'll be doing a different condition for the third. So this is where you have to say, okay, when I'm doing a sampling distribution, is it categorical or is it quantitative? And that's going to dictate a lot of what I'm doing right here. And this one was asking, are you in state, out of state? Just ask somebody that. Are you in state or out of state? And they say, I'm in state. Well, that means it's what? Just put one letter in the chat, and I know you're following along. If I ask you, are you in state, out of state, and you say I'm in state, then I know this is a what type of question. By you saying I'm in state, I know this is a what type of question. I know, but you say I'm in state, I say, oh, then I've asked you this type of question right now. Great, Bridget got it, you got it, categorical. And then now I'm asking you, how much do you pay for your tuition? So if I say, how much is your tuition? You say $22,000 a year, then this is a what type of question. When I say, how much is your tuition? And you say 22,000, just put one letter in the chat. This is a quantitative question. Does that make sense on the difference right here? So this is going to change the way the problem goes with the notation. And when you look at the formula sheet, you'll see different formulas on there. So what do we have right here? And Kayla was pointing it out. What is this right here? We've got things we got to mark. I think people saw that this was N. And so what is 26,000? That is the mean. That is the mean, but be a little more specific. 26,000 is the mean. That is true. It's for all UT students because the registrar told us. So that's for all UT students. So what is 26,000? And this will help when we get to the notation here in a second. So it's for all UT students. The true GPA of all UT students is what? And what is that in notation? Give you a hint. Mu. Kayla got it right there. Mu. And then that makes 7,000 sigma. So now we need to know the notation for this chapter, which is very similar to the last one. It's going to be mu, or the expected sample mean. That's saying if I take a sample of students, what would I expect to see? I'm going to go out and talk to 200 students, so what would I expect to see? Well, if 26,000 is the truth, then, and I'm just writing it down here again, I'd expect to see 26,000. Does that make sense? Like, I know the truth is 26,000, so if I take a sample, I'd expect to see 26,000. Then we need to know the standard deviation. Now, what does the central limit theorem state will happen to the standard deviation? The standard deviation of the distribution of a sample mean, like what we see when we take a sample and we take the mean of it, it'll be water compared to the original mean. And you see it right here mathematically. That's the mathematics of what's happening to it. I think you got it, Nicole. You're getting it. Nicole already solved it. Let's give Nicole and everyone some points there. Nicole looks to have solved it. The new standard deviation, that stands for SD. The new standard deviation is the original standard deviation over the square root of n, which means the new standard deviation will always be smaller to the original one. This is the distribution getting tighter by a factor of square root of n. So you can see here, if we know the notation, if we can find the values, we can then solve. And then what do you think we're going to do if we pass the conditions, which we will do right here? The whole point of this is to do what with these numbers? If you pass the conditions, you can take your mean right here, and people solved this for me. Thank you, everyone, for solving that. I'm going to run this to 495. That's about 495. We go down here to the very bottom, and we put the numbers into the normal curve, and we could talk about what is odd down here or unusual, and we could solve out for how far things are away. So drawing it really helps with solving a lot of these answers. You could, of course, use the equation a sample means distance away from mu y bar is equal to, and then the standard deviation, sigma over square root of n. And that's just literally taking observation minus mean over standard deviation to find a z-score. So if I were to ask you how unusual is, let's say right here, did I put the right numbers in? How unusual is 2700? Who knows how unusual 2700 is? Could you tell me the z-score? You can always rewatch the Kahoot, right? And you do get a formula sheet, which is on the review page. Who could tell me the z-score for, I'm going to probably go here after this question, so I'll grab some food for the Kahoot. Who could tell me the z-score of 2700 while I kind of give you some hints down here on the bottom of the screen? Who could tell me the z-score? You should be able to estimate it a bit. See if you can solve for the z-score, because you're about to get a hint right over here. It's a little, I'd say it's kind of unusual. The z-score for 2700 would be if we take, I'll plug in the numbers over here, and you should be able to get a guesstimate of it. So we're going to go after this question, grab some food. If we take 2700 right here, which is the observed sample mean, minus the true mean, it's true mean right there, for what we'd expect to see. And then we take the standard deviation right here. We should get a z-score pretty close to what? You can print it or write it down. And Kayla, you're on the right track. And it's going to be closer to what? Use the visual to help out, Kayla. You're right there. Oh, great job, people solving. An amazing work. 100 points in the chat. Yep. And the visual should help down here. The visual should help that it's basically a little bit above 2. Always try to draw your visual out here to help on your scratch sheet of paper. And you should get something like that right there. So in the exam, we won't have to find the z. You won't have to find the area. Well, so actually, you know what? This one right here could be a pretty fair, like, find the area question. I'm glad we did exactly this. So here it is. If the test had a multiple choice question at the end of this that said, find the area, and the area was, let's say, A, B, C, or D. We'll put in there in the poll. So find the area. Is the area 0.1%? Is it 2.2%? Is the area 4%? Is the area 16%? So let's ask the community, find the area on this curve right here. Which one of those is it? So we don't have the David M. Lane right now, but I'm just going to keep moving the screen all crazy like. Find the area on the curve using empirical rule right here. Can you do it? And then Brian's going to grab some food. We'll go to David M. Lane. I bet you my guess, one of them, the answer I believe is right, is probably pretty close. So can you find the area of the guess of what it is? How much area is that on the curve right there? Here's what I would do. I'd use your empirical rule numbers of 0, 1, and 2. Giving some hints right here on this. And that's a big hint. That's a big hint right there. So it's going to be, let's check it out. I need to go to David M. Lane. David M. Lane appearing on the screen. And so we're going to put in our mean of 2,600 or 26,000. Standard deviation of 495. And then we're going to go above 2,700. And how close was my guess? If you round up Brian's guess, this is 100 points for Brian right here. Brian's guess was decimal place accurate. If you round up 2.2%. So if you said 2.2%, you would have gotten it. And remember, I solved that without, I've done this a lot. I teach the class, so I mean, come on. But that was solved without using any applet. And how did we possibly guess this? We guessed it because it was very close to the empirical rules number of a positive 2 z-score. So we can put questions like that on the test like this, where we would hope you would see that it's close to 2.5%, and the other numbers there are illogical. I put things that wouldn't occur. Anything above here, I'll show the numbers. The very, very tiny area couldn't be, because this is, according to the empirical rule, this. And so it has to be between these numbers right here. It has to be an area between these numbers. And so it has to be between, you won't use the David M. Lane, correct. So this would narrow it down to only one of these two answers. Does that make sense? It could be, there could be. I wouldn't ask this as a fill in the blank. If I were to ask this question, I wouldn't do it as a fill in the blank. I'd do it as a multiple choice. Because we'd have to accept a pretty wide range of answers. We've asked things like this if you look at the practice test. And let's give one more shout out right here really quickly to the review page. 4, 5, 6. Yeah. No, I know up to 7 standard deviations. I need to review up to 7 standard deviations, but I know the area plus or minus 7 standard deviations. Generally, if you give me a z-score, I can generally tell you pretty good estimate. The hardest part is the center part of the curve, because that's where the numbers change the most. If you're looking for any of the review videos, check these out. But I want to mention this video right here. This video is a big review I did over the different sampling distributions. Man, gosh, so long ago nowadays. But you can see a bunch of example problems worked out, going over different problems, talking about how to solve them, poison or not poison, all this good stuff here, reviewing differences. But Pete, wait, am I saying it? No. Pete. Someone's coughing in the background. P times Q is correct. Awesome. So we'll be started back up here pretty soon. I'm just cracking up at past Brian. P times Q over N square root. P times Q over N square root. When did this video get posted? I've been saying that for 4 years at least. 4.5 years. P times Q over N square root. P times Q over N square root. 4 years of P times Q over N square root. Well, with that, everybody, we'll be back here in just a little bit doing some, let's send out that announcement, but I'll be back in just a little bit. Swing back by. I hope to see a bunch of people here for the Kahoot. Let's practice. Let's get it down. I'll see you soon. I'm going to go grab some food. You should too. Be back in a little bit. Bye for now, everyone. Bye. Kahoot coming up very soon.